basically what I said was that in this, and let me know whenever you can't hear me, just so I can like stop. Like let me know when I pause or break up. I said that there are several parts in the problem that indicate that this problem is with respect to time, that all the rates are with respect to time. And if we know, like if we go back to related rates, that's the definition of a related rate. It's the derivative with respect to time. So you just need to like kind of pick up on those details. They all say changing with time per minute. So that just goes to show that this is related rates. Because I know sometimes it can be hard to tell for some people, but you know, there are several like key factors, and anything that has to do with time should be like an indication. Does that make sense, Julia?
Sometimes like they have other problems that are like, oh, however many people, like however much water entered at 200 millimeters per minute. Like, how do you know? Sometimes it's different.
Sometimes it is different, but I'm going to tell you this. V prime of t is the same thing as dv over dt. Like, that is true. Like, and I know sometimes like it'll look like this and that'll just be like a regular problem. But then sometimes like you have to make it in this form. It's the same thing, but we use this format for related rates. And it's really the same thing. Just know that any derivative that's with respect to time can be made into a related rate, essentially. Not for all of them. Like you're right, there are some problems that are not like that at all. But essentially it can be made into a related rate. And as we see in this problem, I think and maybe it's this one or the other one, the one before, they kind of switch between both. So they're going to ask you for the v prime of t format and then the dv over dt format. You just need to know like how to switch between the two. And they're essentially the same thing. All right, so hold up. Okay, so now we're going to move on to like the actual part. And the only other thing to note is that that wasn't important. It does tell you the formula for the volume, and I've noticed that they always tell it to you, so I don't think you need to memorize it, but just in case, have them ready. Like I think she gave it to us one time, or it's gonna be online, you know, if you ever need it. So at the instant when the radius, give me 1 second. At the instant when the radius of the oil slick is 100 centimeters and the height is 0.5 centimeter, or half a centimeter, the radius is increasing at a rate of 2.5 centimeters per minute. At this instant, what is the rate of change of the height of the oil slick with respect to time in centimeters per minute? All right, so the first thing I would do is just decipher the givens that you've been given in this example. All right, so we know that dv over dt is 2000 just from this part right here. Now I'm going to take what we were given in part A. So it says the radius is 100 centimeters. That's one thing. It says the height is half a centimeter. That's another thing. It says the radius is increasing at a rate of 2.5 centimeters per minute. So dr over dt is 2.5 centimeters per minute. And it's asking us, what is the rate of change of the height with respect to time? So it's asking us, what is dh over dt? Now, to get this, and normally, this is just like a side note. Whenever you're given something like this, I believe this is what it would look like, a right circular cylinder. You just need to know that R and H are proportional. And that will help you figure out if, for example, let's say that you weren't given R, right? Julia, are you following along?
Yeah.
Right. So if you're not given R, what are you gonna do? You have nothing to plug in for R. You have to make the R's an H. And we know that R over H would be some number over another number, and that's how you'll do it. Is that kind of like bringing back some memories, Julia?
But like, I don't know. What if they do that? Then where would I find R?
Well, R, we know that R and H are proportional, and in a problem like this, actually, I'm gonna wait until the next problem, only because I think for that problem, it's like it's asking you to do that process.
Okay.
So and if anything, I'll just like go over it because that one is more clear because there's actually like an image there. So for now, all we know is that we're given all that. So you're pretty much good. Like you have, if you look at this formula, we have dv over dt right here, and I forgot to write the d. You have dv over dt, we have r, we have dr over dt, we have h, we have dh over dt. So pretty much we're good. So now you write the formula you're given, and then you take the derivative with respect to time. So dv over dt, and this is going to be product rule because it's two variables. So that just becomes 2 pi r dr over dt h, because that's the second part, plus pi r squared dh over dt. Julia, do you get that? Like, do you understand that derivative?
I think so.
Okay. So once you have like your formula, all you have to do is plug in. And that's like really the more simple part of it. So that just becomes 2000. The 2 pi, that just becomes 100 centimeters. We have a dr over dt next, so that's 2.5. That's 0.5 because of the h, plus, and then it becomes pi. Then we have an r squared at 100, so 100 squared. And then that's dh over dt all over there. And I know like that's super long, and I believe that for this problem we did have access to a calculator, only because that is kind of like, and even then we have access to the calculator either way. So when you move everything over, remember, like, we're moving things over so that we're like left with that. Just know that like you would have to move, I'm gonna clear the givens just so it's clear as to what I'm doing. You're left with, it becomes 2000. You have to subtract everything that's like right here. So it's like 2 pi 100 times 2.5 times 1/2, because it's 0.5. And then you just divide by pi times 100 squared, because this here is in front of this. So that's kind of like what you're left with. And that's what dh over dt would be. And
Wait,
then you want,
wait.
what?
So you're trying to move all that other stuff in front of dh over dt to be. Never mind. I get it.
You got it?
Yeah.
Okay, that's your answer. And that simplifies, just because that's what I have written down on my paper. It's like 0.03866, something along those lines. And the only other thing that you would have to add in order to receive credit is the unit of measure. And Julia, I want you to tell me the unit of measure, okay? If we're left with height, which we know it's in centimeters, what would be the derivative of height?
The derivative of height, centimeter
Yes.
squared.
No, remember when you're adding the derivative of height with respect to time, you're adding a unit like on the bottom. Like you're not just squaring the unit like the top, like the centimeters. You have to add something to the bottom. Centimeters.
Minute?
Did you say per minute?
Yeah.
Yes, that's correct.
Okay.
Think about it. Look, and this kind of will be a guide. What is h? It's dh over dt. So h over t pretty much, which is centimeters over minute. Does that kind of make sense?
Yeah.
All right. So, and that'll kind of help. That's how you do part A. A recovery device arrives on the scene and begins removing oil. The rate at which oil is removed is RT, that function, cubic centimeters per minute, where T is the time in minutes since the device began working. Oil continues to leak at a rate of 200 centimeters per minute. Find the time T when the oil slick reaches its maximum volume. Justify your answer. All right. So, when, like, at least I'm thinking of this, I'm gonna go back to what I said earlier. It's asking us to find the maximum volume. Whenever we're trying to find the maximum, we take the derivative and set it equal to 0. But didn't I just say that dv over dt is the same thing as v prime of t?
Yeah.
Yes, it is. It's the exact same thing. So in this problem, at least, you just know that you have to set dv over dt equal to 0. But there's an added part to dv over dt. Now is where the rate in, rate out comes in. And it reminds you of that when it says the rate out is this and the rate in is that. So like there's oil leaking and that's like 2000, but then there's like a device that comes and like sucks it up and that's RT. So your rate in is the 2000, your rate out is the RT. But remember, those are both rates. Rates kind of matches with V of t. Or rate doesn't match with V of t, it matches with V prime of t. Right? Does that make sense, Julia?
Say that part again.
The rate in and the rate out are example, like they're in centimeters cubed per minute.
Okay.
So when you're like, you know how one time you told, like you set the equation, you did like 2000 minus R of t?
Yeah.
Okay, you get that. I remember you did that. But
Yeah.
with 2000 of RT, would it be V of t or would it be V prime of t?
V
And you just
prime.
have to think about the units for both of them. Which of the units matches up? The units for this is centimeters cubed. The units for this, as you told me, it was centimeters cubed per minute. So which one would be the same?
The V prime of t.
Exactly.
Wait, why is it? Never mind, I get it.
You get it?
Hey, yeah.
And you just need to make sure, like, because I know some, like, in that one FRQ we did, just make sure you're matching up the units as you go on, just to, like, prevent yourself from making a mistake. And you know that volume is just centimeters cubed. Volume is anything cubed, pretty much. But the rate of volume, especially with respect to time, becomes centimeters cubed per minute. And that is what matches up between those two. So basically, from that knowledge, we know that V prime of t is equal to 2000 minus R of t. Basically, the rate of the volume is the rate in minus the rate out. That's what it is. And that's just like a fact. And it tells us that V prime of t or dv over dt is the same thing. If you want to just stick with that notation, it's 2000 minus 400 radical t. I'm plugging it in. And then remember, to find the max, we have v, we take the derivative, we set it equal to 0. So now we have the derivative already. All we have to do is set it equal to 0. 400 radical t. So then I move this over here. You divide by 400 on both sides. You're left with radical t is equal to 5. And in order to get the t, you just square. So t is equal to 25. And if you want to be more specific, minutes. That's like our critical number. But remember, when we're trying to find the maximum volume or the absolute max, we have to do a chart. Or we can do, I know that at least for this problem, they didn't require you to do the chart. But essentially that's what you would have to do. But since at least like looking at the problem, there's no interval. And this is probably just because it's like one of the older problems. Like I noticed that as you get to more of the new problems, it aligns with more of what we're doing like presently. So that's just like a mistake. But in the rubric for this problem, they basically they kind of told you that since let me look at this. Since dv over dt is increasing, since hold up, sorry. Give me 1 second. I'm trying to figure this out. Hold up. Okay. What is happening? Julia, can you hear me?
Yeah.
It's like glitching. Okay. I think I figured it out. Okay. So this is kind of how they're asking you to solve it. Right? So it's asking you kind of for the absolute maximum volume. But we know that by using like our number line, okay? So you don't have to do a chart for this one. Normally do the chart, but for this one it's a little different. So I'm gonna clear this. You have it,
Yeah.
Julia? All right. So our critical point is t is equal to 25. When we do the number line, we're looking at v prime of t. If you look at the v prime of t that you wrote at the top, you know that it's 200 minus radical t. So when you plug in a number like under it, I'm gonna plug in. It was 400. I'm gonna plug in 16 only because I know that's a very simple like radical. 200 minus 400 times 4. That just becomes 2,000. Saying that wrong. Minus 16,000, which is 400, which means that this is positive. And then when you go beyond, I'm gonna plug in 49, or what's the next one? 36. That one's closer. So 2,000 minus 436. And Julia, whenever you're plugging in numbers like to do the test, try to plug in like the most convenient numbers. Like it doesn't have to be 26. It could be 36, because you know that goes into the radical very easily, and it still meets the condition. So it doesn't always have to be the number that's right after it. So 2,000 minus 400 times 6 is just going to be negative. I know that. So then it changes from positive to negative. So we know it's a relative maximum at least. But if you kind of do the graph in your head, since we know that dv over dt is positive here, it's going to be like increasing, and then it's going to go here and then start decreasing. So I guess by that logic too, they assume that it'll reach its maximum too, and I believe that in the problem, and it's only because let me just think about this for 1 second. Thinking. And yeah, I think I really just do think that by doing that, that's enough logic for them. But just know that for this type of problem, this is how they did it in the rubric. But for this type of problem, I think that like for our actual AP test, they're going to be asking us to do the chart, which is you do the critical numbers, you do the endpoints, you do all that. And that's kind of like the correct way to do the maximum, at least like with more recent terms. So just expect to be doing that instead of this. So basically all you would have to say is that the maximum occurs at t is equal to 25. Julia, is that good?
Yeah.
And then of course say because v prime of t changes from positive to negative. And I think that's enough reasoning because it's a more simplified rubric. Now moving to part C. Oops. Okay, wait. Let's see. Part C. Give me 1 second. All right. So by the time the recovery device began removing oil, 60,000 cubic centimeters of oil had already leaked. Right, but do not evaluate an expression involving an integral that gives the volume of oil the time found in part B. All right, so remember, what we had was this. That's our rate. But in order to get the volume, we have to integrate. We have to go down. And obviously this would be v of t, but now we have to integrate this whole thing to get it. And that would be part of the answer. So whenever you're integrating, you also have to consider what you initially start with. That's what you always start with. And it tells us that it starts with 60,000 cubic centimeters. So that's the first thing I'm going to write. less. And then when you think about it, that's kind of like your c, because when you take the derivative, this goes away. But we're kind of like adding back the c that we got taken away when we took the derivative. So that's kind of where that kind of comes from. And so now that we're adding the original volume that we got, now all we have to do is integrate this little section right here. So it goes from 2000 minus r of t, and don't forget the dt. And then let me just double check. I think that that would be good, but then it also says write but do not evaluate an expression that gives the volume of the oil at the time found in part B. Or right, the time we found in part B was t is equal to 25. So basically it's saying like find the amount of oil that is present at part B, like at time is equal to 25. And we know that by adding the 60,000 and then accounting for the rate in and the rate out this time, we'll find the total amount at t is equal to 25. So the only other thing I would add are the bounds. You can have negative time, so it's obviously going to start at 0. Always remember that. And it's only asking for t is equal to 25. So that's kind of where that one would end. And does that make sense, Julia?
Yeah.
It does?
Yes.
All right. So let me just update this little document really quickly, only because I didn't have time to do it after our Guay's session. So let me just kind of do it, and then I'll share it with you guys quick. So let me just stop sharing this one with you guys, only because I don't think it'll update, and then I will share it. Julia, did you have any other questions about that problem at least? Just like feel free to say it.
No, I'm okay.
Okay, just make sure, because I know that like sometimes like you won't say it because like there's people, but it's really just Aaron, Jamie, and you. So yours should be good. All right, so get 2003 Q5 ready, and I'll share it right now. Okay, so this is right here. Right, so now it is updated. So, okay, so this is 2003 Q5. Did that by accident. But yes, it is 2003 Q5. Okay, so this is another related rate problem, and it actually is the same volume. It's a cylinder again. So this is just added practice with that concept, but now instead of doing rate in, rate out, we're going to be doing differential equations, which is, as Ms. Q said, it's probably going to be the most heavily weighted part of the exam for the 2020 year. So let's read it.
Why do you lie?
What?
Why?
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 Only because differential equations are like, maybe I would say like the most centermost point of AP Calculus AB. It's obviously limits, derivatives, integrals, and differential equations allow you to like, differential equations kind of written like that, they allow you to like shift between the derivative and the integral like very easily. It's like a very like common process, because you know that when you're doing the derivative, it's just in this form, but then when you do the integral, you move the dt to this side, you know, you have the dv there, kind of like that. I think it's along those lines. So it says a coffee pot has the shape of a cylinder with radius 5 inches as shown in the figure above. The figure is on the next page. Give me 1 second, just because didn't save right. All I have to do is share it again. And just so you can see the figure as we go through it. but you guys see it in front of you, but just so I can like annotate it there. So the coffee pot has the shape of a cylinder with radius 5 inches, and it indicates that on the diagram right there. That's R. And as shown in the figure above, let H be the depth of the coffee in the pot, and H can also be interpreted as height, essentially, measured in inches, where H is a function of time of t. That's your first indicator, Julia. It says it's a function of time t, so it's already with respect to time. That's just like already like a signal, measured in seconds. The volume of the coffee in the pot is changing at a rate of -5 radical H cubic inches per second. Again, the volume V of the cylinder with radius R is that. Okay, so it tells us, I'm going to tell you what it says, and just so you can write it down. It says that H is changing with a function of time, so there is a dH over dt. It's telling us that V is equal to pi r squared H. That's just the formula. And then it also says that dV over dt is -5 pi radical H. So that's what is given from this problem. Okay, so now moving on to part A. Do you have all that written down?
Yeah.
All right, so moving on to part A. Clear? Right. So it says that show that dH over dt is negative radical H over 5. So this is, it's telling us the answer. We just have to make sure that our answer looks like that. And that's like the big, I would say, or maybe like the hardest part of this type of problem, only because you just need to know that really you need to know that the process of differentiation and solving things and doing things like that in order to get that, and then being able to move things around in order for the answer to look like this. Okay, so the first thing I would do, I would write this formula right here, the formula that we were given, because in order to get to dH over dt, you have to notice that we're gonna have to use that H that's right there. And then the next thing I would do, and this is really important when you're doing related rates, you need to know when something is changing with respect to time or where things are staying constant. And in this problem, the radius, and this is gonna be, it's maybe like harder for some problems or easier for some problems, but in problems like this, like the radius of the water that's increasing, that's growing, filling up, or decreasing, because I think it's leaking in this problem at least. The radius is always going to stay the same. Does that make sense?
Yeah.
Because like as you like fill up this container, as you like fill up a tub, for example, like the width or the radius, it's going to stay the same, only because like water increases at a level, or like it's very like it's slightly concave, but it for the most part it increases at like a very level like balance. So essentially, since 5 is going to be the same at like t is equal to 1 second, t is equal to 5 seconds, or infinity pretty much, your dr over dt would be 0. So it's not necessary. Which means essentially 5 is going to be constant throughout the time. So you can plug in 5 here because it is a constant. Does that make sense? Since 5 is constant throughout all of time, it becomes a constant. Does that make sense, Julia?
Yeah.
Okay. And whenever you have a constant number, just plug it in already, because it's not going to affect. You're not going to have a rate that goes with that. So it essentially wouldn't be impacted. So since 5 is a constant, since 5 is a constant, we can just simplify this to v is equal to 25 pi h. And then from there, now we can, take the derivative, find dH over dt, and do what we know. So clear this. We know that v is equal to 25 pi h. And Julia, you're going to tell me how to take the derivative of this.
Okay.
So what is it?
Wait, the derivative of 25 pi h?
Yeah.
Okay, dv over dt
Okay.
equals
I'm sorry. I started writing it.
25
Pi. Remember, because pi is a constant. And then what does the last part become?
dh over dt.
Yes. Okay. Now I want you, and you're gonna guide me through this. I want you to plug in the constant that we know. And what's the one thing that you see that you can plug in?
What dh over dt is.
No, because we don't pretend you don't have this. We're trying to prove that it's equal to that. But we know this. So what is that?
That's negative 5 pi radical h.
Okay. And then what would we have to do now in order to get that answer?
One. Divide by 25 pi.
Okay. So then you're left with 5 pi radical h 25 pi. But what does that simplify to?
To negative 5 radical h.
Over 25.
Yeah, over 25.
And then what can you do one more time?
Divide the negative 5 stuff.
Well, you can notice that, like, really, 5 over 25 here can simplify to 1 over 5, which just becomes, and I wrote this little part wrong. It's an h on the inside. But really, it just becomes negative radical h over 5. And that's the answer that they told us to get. Does that make sense?
Yeah.
All right, so I'm going to clear it and move on. Given that h is equal to 17 at time t equals 0, solve the differential equation dh over dt for h as a function of t. And this is why I'm telling you, like, oh, they like to use this type of problem, because now whenever they say solve the differential equation, it's asking us to move the dt to the other side, do all that stuff with the integrals. But that's a whole different process than taking the derivative. Derivative and integral, two different processes, but they can both be kind of merged together with differential equations, pretty much. Mostly with anything, but at least with this type. So it tells us that h of 0 is 17, because h is 17 when t is equal to 0. So now that's like our given, like our particular solution at least. And now all we have to do is find like the stem of the problem or the equation. So I'm gonna guide you through the process. So dh over dt is negative radical h over 5. Make sure that your variables are on the right side. You can't have like things mixed together. So what I would do is move the dt to this side, and I would move the radical h to this side. So you're left with negative 1 over 5 here. And then at this point, now you can take the integral. I made a mistake. And this is just so it's going to be clear. Just so that you don't make the same mistake I did. So the first thing I do is move this over. I keep writing things wrong. I move the dt over. But now I want h to be on the other side. So you have to divide by 1 over radical h on both sides. And I accidentally wrote it as just radical h, but in reality, it's 1 over radical h. And if you do that kind of simple math, I think it prevents you from making a simple mistake like that. So now we can integrate. The first thing I would do is simplify this to negative 1.
It's not negative 1.
Huh?
It's not negative 1 radical. Negative 1 over radical h.
Honestly, both ways are simple, but the reason I didn't move the negative over, Julia, is because I see this is like whenever I want the negative to stay on the side that has the easier integral. And this is a very easy integral. Like negative 1 over 5 is just that. Let's see. So do you see like how that's kind of simple, and then moving over the negative might make you confused with the negative that's like right over here? Does that
Yeah.
kind of make sense? Yeah. So that's kind of what I wanted to avoid. So now that we have this, we still have to take the integral of this. I moved the -1/2 to make it more, like, to make it not a fraction, basically. So to continue, I'm gonna clear steps that I did at the beginning, just so you can see the process still. So the integral of h to the -1/2 becomes h to the 1/2, because you're adding 1, and -1/2 plus 1 is 1/2 over 1/2. And you don't need to write it plus c again. It's only once. 1/5t plus c, which later simplifies to basically 2 radical h is equal to -1/5t plus c. Okay? I'm going to continue. Now at this point, I think it would be smart to solve for c. And whenever you solve for c, you have to use the solution it gave you at the beginning. It told us that h of 0 is equal to 17. So I'm going to plug in the 17 here because that's the h. I'm going to plug in the 0 here because that's the c. And then we're left with c is equal to 2 radical 17. Okay, so now I'm going to write that here just so I can finish the problem off without having to keep erasing. So at this point, we use our stem that we got before, and now we plug in the c that we just got. So using the c we just got, 2 radical 17, I'm actually going to put 2 radical h is equal to -1/5t plus 2 radical 17. Okay, now all we have to do is move things over and just simplify, just because it has to be in terms of h. And it says that because, right, h is a function of t, so it needs to be like everything equal to h. So the first thing, I would divide by 2 or multiply by 1/2 on both sides. That's ugly. But so you're left with -1/10 t plus radical 17. Right? And then now, in order to get rid of the radical, all you have to do is square on both sides. So you get that h is equal to -1/10t. Remember to square everything. And that's just all squared. And then don't even bother trying to factor that out. That's perfectly fine. Okay? Does that make sense, Julia?
Yeah.
Okay, good. And now the last part is, at what time t is the coffee pot empty? Okay, so since we just solved for h, just know that the coffee pot is empty when the height is 0. Does that make sense? Because when your coffee pot has completely leaked all of the coffee, really it's truly going to be empty when there's no more coffee in it. And there's no more coffee when it's level to the ground. There's 0 height. So we just solved for height. We just got that height is equal to -1/10t plus radical 17 squared. Now, to solve for the time t when it's empty, all we have to do is make the height equal to 0. So you're left with -1/10t plus radical 17 squared. So the first thing you can do is just square on both sides. That's really just nothing. You can just cancel it, but if you want to show that step, go for it. And then I would move the -1/10t to this side. So you're left with this is equal to radical 17. And make sure to try to like differentiate between your t's and your pluses. It's easy to do it on paper, but that's an important thing. And then lastly, all I would do is just move the 10 over. So at time, 10 is equal to 10 times radical 17 seconds. Do not forget to write the unit because it's asking for a specific time. The coffee pot will be empty. And that's the answer.
-1 and -1/10.
What?
It's -1/10.
Yes, but I moved it over here.
Oh, okay.
Yeah, that's what I did. Only because you technically can move the negative radical 17, but then there's two negatives and they cancel out.
Okay.
Does that make sense?
Yeah.
All right. And this problem, honestly, like I'm not perfectly sure that they would give something like this, only because they probably will. Like they probably will ask you to move over the variable, integrate, do things like that, only because you can't show those steps on the calculator, if that makes sense. And that's why they prefer differential equations over something like this, because that you can kind of put into a calculator. By this, you have to use separation of variables, you have to integrate, it's like a longer process. You have to integrate both sides. I think they would rather do something like that over, just a simple v prime of t. Does that make sense?
Yeah.
All right, so that's it. There's only 3 parts of that question.